Thank you for joining me for some more reinforced concrete design. In this session, we will look at punching shear, what it is, why it happens, and how the Eurocode deals with it. In this slide, you can see several examples of punching shear failure of flat reinforced concrete slabs supported by columns. The design of flat reinforced concrete slabs is usually based on a 1 meter wide strip. The shear design of flat slabs is also based on the variable strut inclination method, which we previously discussed. Shear stresses in flat slabs subjected to uniformly distributed loads are usually small and can be taken by the concrete depth of the slab. Therefore, the shear reinforcement is seldom required. The design should ensure that the applied shear is smaller than the crushing strength of concrete, and heavy concentrated loads do not cause localized punching shear failure. In contrast to the vertical shear design of beams, the design of flat reinforced concrete slabs for punching shear failure is based on shear stresses rather than shear forces. The applied design shear force VED and the design shear resistance of the slab without shear reinforcement VRDC are converted to the design shear stress by redistributing those forces over a certain shear failure surface. During punching shear failure, the concentrated load causes shearing stresses on a section around the load. The possible sources of concentrated loads can include a supporting column, a wheel of a heavy vehicle, a support of heavy equipment, and so on. Here you can see an example of punching shear failure of a flat slab around a column. The punching shear design is based on the critical surface encompassing the concentrated load applied as shown here. The critical surface is located at two effective depths of the slab from the perimeter of the loaded area. The punching shear resistance of the slab can be calculated as the design maximum shear stress, VRDC, times the area of the critical surface, which is equal to the average effective depth of the slab times the control shear perimeter, U1. The design maximum shear stress, VRDC, equals to the expression given in this slide. Here, the parameter K represents the effect of the depth of the slab on its shear resistance, and the parameter ρL is the average reinforcement ratio found as a square root of the product of reinforcement ratios in the two directions of the slab. The design shear force should be smaller than the crushing resistance of concrete VRD max at the face of the loaded area. VRD max can be found using the expression given on this slide. In this expression, μ1 is the reduction factor for concrete working in shear, and ULA is the perimeter of the loaded area. The mechanism of the punching shear failure of the slab is often misunderstood. Here you can see the misconception of the punching shear failure surface, which suggests that the surface is vertical and correct representation of the included failure surface. The inclined shape of the failure surface is supported by the evidence from slabs collapse due to punching shear failure. Therefore, the control perimeter is located away from the loaded area. Eurocode 2 defines the distance between the loaded area and the first basic control perimeter equal to two effective depths of the slab, which corresponds to the failure surface inclination angle of 26.6 degrees. When the applied concentrated load is very large, additional control perimeters located away from the loaded area should be checked. The shape of the control perimeter depends on the shape of the loaded area and its location in the slab. Here you can see examples of the shapes of the loaded area and the corresponding control perimeters. When the loaded area is close to or at a slab edge, the control perimeter is cut by the edge. When the concentrated load is located closer than 6 times the average effective depth of the slab to an opening, the control perimeter should be reduced based on the geometry and orientation of the opening and the distance from it as shown on this slide. When the resistance of an unreinforced concrete slab is insufficient, punching shear reinforcement is required within the outer control perimeter. The length of the outer control perimeter at which the shear reinforcement is no longer required is calculated as the applied shear force divided by the design maximum shear stress in concrete and by the average effective depth of the slab. When the outer control perimeter is located further than 3 average effective depths from the loaded area, punching shear reinforcement is placed in the zone between half of the average effective depths from the loaded area and 1.5 of the average effective depth inside of the outer control perimeter. When the outer control perimeter is located closer than 3 average effective depths from the loaded area, punching shear reinforcement is placed in the zone between 0.3 of the average effective depths from the loaded area and 1.5 of the average effective depths inside of the outer control perimeter. Vertical links are often used as punching shear reinforcement. They're normally provided around at least 2 perimeters. The maximum radial spacing of links should not be larger than 0.75 of the average effective depth of the slab. The maximum circumferential spacing of links within the perimeter outstanding at least 2 effective depths from the loaded area should not be larger than 1.5 average effective depths. The maximum circumferential spacing of links within a greater perimeter should not be larger than 2 average effective depths. There are a few different methods for the arrangement of links around the loaded area. Here you can see 3 examples, including radial arrangement, band arrangement, and uniform arrangement. The area of punching and shear reinforcement ASW required within a certain perimeter U1 around the loaded area is calculated based on the applied punching shear stress VEDCS, the radial spacing of links SR, and the effective design strength of shear reinforcement. Note that punching shear reinforcement can be inclined and arranged across the punching shear failure surfaces. This is considered by the angle alpha between the shear reinforcement and the plane of the slab. In the case of vertical links, sinus alpha equals 1, and the expression for the area of punching shear reinforcement is simplified. Note that the term 0.75 times VRDC represents the contribution from the concrete slab equal to 75% of the design maximum shear stress of an unreinforced slab. The area of an individual link leg should not be smaller than the minimum area that is calculated depending on the concrete and steel yielding strength, as well as on the radial and circumferential spacing of links. And that concludes our focused look into punching shear design, including critical perimeters and detailed reinforcement, ensuring slab column robust connection safety.